Bryan is here from Canada. He's flying the flag proudly on his T-shirt. Bryan's a Node Core contributor. I've got my notes in my book and I'm not looking at them. This is terrible. So you're going to talk to us now about what?
Native code.
Right. On you go. Speak to you soon.
All right, folks. So yes, native code, but more in particular, a new way to call native code in Node.js. First of all, thank you all for being here at this early hour, especially given the karaoke and whiskey tasting last night. I'm sure everybody's still recovering a bit, so thank you very much for being here. So yeah, I also wanted to call out the conference organizers. They've done a very fantastic job, so kind of big round of applause to them. Although in the early agenda, when it was first published, this talk was entitled A New Way to Call Native Code in English. That would be cool, but you know. Right, so I'm Bryan English, BENGL on pretty much every internet service, your Twitters, your GitHubs, and so on. I'm an engineering manager at Datadog. We work on the APM client library for Node.js, also C++, also Lua. Long story, love to talk about all the intricacies of all those languages being involved later on with whoever's interested. I'm also a Node.js core collaborator and releaser a couple of times. My pronouns are he, him, and his, and yes, I'm Canadian and I live in New York City, so that's me. Okay, so yes, I do work at Datadog, but most of the content of this talk is not stuff that I did at Datadog. This is on the side stuff. I am an engineering manager. I don't write a lot of code anymore, to be honest. That said, we did have a little bit of time at the office to work on some of this stuff as part of like a hack day kind of stuff. So yeah, that's just a little bit of context of where this fits in with me and my work. Also, I should say we're hiring. Okay, so what am I talking about today? Foreign function interface. This is the crux of everything that I'm talking about today. I was trying to find a good definition of foreign function interfaces. The best one I could find was on, of all places, C2 Wiki. And the definition I found was a foreign function interface is an interface that allows calling code written in one programming language from another that is neither a superset nor a subset. So we're not talking about like calling JavaScript from TypeScript or something like that, right? We're talking about two completely different languages, right? So primarily in Node, we're concerned with calling calling C++ or Zig or C or Go or any other native language from Node, from inside the JavaScript engine. So why would we want to do this? You know, often these days we say like Node provides all these great APIs for interacting with the system so that we don't need any native code, right? So why would we want to do this? And the answer is that native code exists. There's plenty of native code in the world and we need to call it from time to time. Sometimes it needs to exist. Sometimes we need to have it in that place. And sometimes it's just the easiest solution. All of programming is trade-offs. It's trade-offs all the way down. And sometimes this is the correct trade-off. So here are some examples of like why we would need it. One is there are proprietary native APIs where we're starting off in Node.js, we're calling some native add-on, and even then that is calling some proprietary API that we don't have the source code to or something like that, so we can't just tie it all together. There are a few very obvious examples of this. One is the Oracle database library as it is in Node. In order to get the full functionality from it, it actually has to do exactly that. So when you npm install Oracle DB, it basically depends that you have the Oracle database drivers installed on your system separately, not through npm. So that's being called separately. So every time you do one of these kind of things, create a connection, execute it, it's going through all those layers. Okay, so that's one reason we need native code. Another interesting one is there are a bunch of V8 APIs that are not exposed in Node.js. Today, there are plenty of them that we have access to, but there are still some that aren't available just in Node.js without calling into native code. For example, in APM tools like ours, we need some of these from time to time. But today we have such a great set of APIs available, so this isn't that much of an issue anymore. For example, we have all the heap snapshot stuff, GC statistics, all this good stuff, even promise hooks. So there's not much missing today, but there are still a few things. Another interesting one is things like libc APIs or system calls that are not exposed in Node.js. Of course, Node.js exposes a lot. We have a lot of the system access we could ever want, but some is not there. So for an example of that, sleep. Sleep is a very basic thing that's available in many programming languages. In Node, we typically do something like a set timeout, and that's an asynchronous call. But what if you really, really, really wanted a synchronous sleep? Okay, yes, there are ways of doing that in Node.js using atomics. We can talk about that later if we like. But in order to do this using the libc call, the libc function sleep, we need to do this using native code if we really wanted to do that. That's a bit of a contrived example. A less contrived example would be something like execvp. So the exec family of functions basically allows you to swap a process for a completely different process. So if you're familiar with how Node.js and various other programs spawn child processes, the way they do it is by forking, so basically splitting the process in two, and then calling exec in order to swap the second process with the one that is intended. This is true on Unix systems, not the same everywhere, but this is something that you may want to do for various reasons. For example, in bash, you actually have access to this command directly with the exec command in bash. So if you're writing a wrapper script that needs to set up an environment of some kind, maybe some environment variables, maybe some arguments, something like that, and you want to not have that bash process around, you can just call exec. You can't do something similar in Node without writing some native code. So that's another reason. Okay, so let's talk about sockets. There's lots to talk about sockets yesterday. Thanks, James and Aaron. So typically when we're talking about sockets, we're talking about either internet sockets, internet domain sockets, or Unix domain sockets. For internet domain sockets in stream mode, it's basically your TCP IP connections, right? So in Node, we have access to that. It's very simple. It's net.connect. So that's built into Node. That's very simple. Another one would be Unix domain sockets, again, in stream mode. Net.connect provides the same API for you. It works just fine. So then for datagram sockets, we can again use those in the internet domain using dgram, the dgram library built into Node. But what about Unix domain sockets with dgram? No. We don't have that in Node today. There are a bunch of reasons, mostly involving Windows. But in order to do dgram Unix domain, you need to use a native add-on today. It's called Unix dgram. It's not built into Node, so we actually need that today as a separate add-on. Another reason why you might need native code is to do things faster than the JavaScript engine can do. We've got Yegis and Daniel, who will be on right after me, who are going to talk about some of that. And but basically, the idea here is there's all kinds of things that you can do in native code that maybe JavaScript engine won't be the best at. For example, there are many memory management things and other things like SIMD that can happen, right? So that's another reason. Okay, so we've established, yes, there are a bunch of reasons why you need to call native code. So now I'm going to talk a little bit about the history of calling native code from Node. So in the beginning, we had native add-ons, and we still have these today. So just as a simple motivating example, this is a C function that is just adding two double precision floats together. Very simple. This is just an example, right? So given this function, how would we call this from JavaScript? So with native add-ons, we'd have this kind of mess of code, right? So first of all, we have this, I've included the function itself, so we've got that double add, double A, double B, all that stuff. And then we have the next function, which is actually the C++ implementation that is grabbing the arguments. First, it's grabbing the isolate, which is some internal stuff that, probably you wish you didn't have to know about. And then we're grabbing the arguments, we're making sure they're numbers. This is actually skipping a whole bunch of type checking code, kind of waving hands around that, then grabbing the actual value out of that. Then we have to take that, the function callback info, which is basically V8's representation of pretty much the call site, right? And then we're going to get the return value, we're going to set it. Okay, this is a mess. There's a lot of stuff going on here. If you don't do C++ every day and you don't work with V8 every day, this stuff can get very confusing. And at the bottom, there's even more with initializing the module, right? It can be slightly painful. But if you do it often enough, this becomes second nature. So in 2017, an interesting API was added to Node. It's called Node API. I think there's a few folks who started this effort in the room today. I can see a few of them, so thank you folks for adding this. But basically this takes this one step further and creates a stable ABI across versions of Node, which is fantastic. It means we don't have to rewrite all of what you just saw many times, and instead you use the Node API version of it instead. Not much changes here. We still have to do a lot of the initialization stuff, take apart the arguments, this kind of stuff. But at least we get a little bit more stability out of it, which is fantastic. Okay, we're going to rewind a little bit in history. Sorry, we're going to go back and forth like, I don't know, Doctor Who or something. But so now I'm going to talk about FFI libraries, right? So Node FFI, that was released in 2011 by Too Tall Nate, Nathan, can't pronounce his last name, not going to try. But with this approach, you can have your C code and you don't need all of this wrapper code in C++, right? Instead, we're basically loading the dynamic library in and then providing the function signature, and that's enough for an underlying FFI library, in this case libFFI, to make the function call into, again, in this case, our adder function. So right there at the bottom of the slide, you can see it's just calling it directly, adding two floating point numbers together, and we get 5.5. Fantastic. So this is an approach I really like because I don't really like writing C++, let's be honest. So this is the kind of approach that I would love to see built into Node, and we'll get into that a little bit later. So in 2018, so this is about a year after Node API was first introduced, this library was actually rewritten by Anna Henningsen to take advantage of Node API. So now we have both that stability and FFI as a concept here. So basically, when I say FFI, basically from here on out, I'm not talking about any interface. I'm talking specifically about ones that allow us to reduce the amount of C++ we have to write. And reduce the need for extra native add-ons, like in that Oracle example I gave earlier. Okay, so we have that one. An interesting question here is, why is there an underlying FFI library? What does that mean? What is that used for, right? Pardon me. So native function calls are basically standardized as something called calling conventions. And compilers basically are one of the things they do is they build these function calls for target architectures and operating systems using these calling conventions. So if you don't have a compiler involved, you basically need to create this whole thing dynamically on the call stack with the registers and stuff in the right place. It's a complicated process, and it needs to be different for every architecture and operating system. So just to give you an example of how deep this rabbit hole can go, here we have two different calling conventions on Windows. And you can see this gets pretty interesting pretty quickly. One of the questions is, who clears the stack after a function call? So it's different in both of these. There's where do things end up in terms of registers or stack and that kind of stuff like I just mentioned. This is a pain, right? So we have libraries like libFFI in order to do that work for us. So libFFI was a library created by Anthony Green. It's used in a bunch of different programming languages as like the official FFI interface. And you know, it made for a great base to build an FFI feature into Node with for Nathan and for Anna to build off of. One of the great things about the library is its support matrix. So remember I was talking about the different architectures and operating systems. This is a very, very small portion of the list of what it supports. It supports operating systems that I've never heard of. It supports architectures that don't exist physically. So like it supports damn near everything, and that's one of the reasons why it's an appropriate thing to use here. So why aren't FFIs more popular in Node.js, right? Today, if you look at almost any native code in any NPM module, it's almost always using a native add-on. Why aren't they using one of these existing FFI libraries, for example, in order to make things easier? So there's basically two core reasons for this. One is that these libraries can be pretty slow, or at least perceived as slow, for a lot of use cases, right? So if you're dealing with very performance-intensive code, the kind of code you might dive into C++ for, you probably don't want to add too many layers of slowness to that, right? So that's one main reason. Another one is, in order to use any of these FFI approaches, now you have another dependency. And if you've worked with Node, you know that yet another dependency is not necessarily something you want. The tree is already very big usually, right? So most folks want to avoid that. So that makes sense. Okay, so now we're going to get to where I started getting involved. 2020 was fun. It was an interesting year. So during that year, in order to sort of get my mind off of things, one of the projects I worked on was a book called Multi-Threaded JavaScript, which I worked on with my colleague Thomas Hunter. And so one of the things that obviously comes up when you talk about multi-threaded JavaScript is things like shared array buffers, right? So shared array buffers are pretty much exactly what they sound like. It's a chunk of memory that you're sharing between two threads, right? And so basically, given that concept, I was wondering if that could be used in order to optimize things in terms of FFIs. So I took this approach of shared buffers, basically, and tried to apply it to FFI systems. So what I ended up doing is building an FFI library called SBFFI. I'll show how that works a little bit later. But the interesting thing to me is how it's implemented, right? So rather than having a lot of decomposition of arguments and, you know, making sure types are correctly on the C++ side, it moves most of the type checking and stuff to the JavaScript side, and instead just relies on a single chunk of memory, basically a struct that contains, first of all, a pointer to the FFI library's definition of the function, basically the function signature, which it can then use to actually build up the function call. And then the second thing in this buffer is the function pointer itself. So that, you know, for those who don't do a lot of C or C++ or native code, if you don't know what pointers are, it's just a memory address, okay? So this is the memory address of the function so that the FFI library can then execute it, right? So then we've got slots for both the return value and the arguments. And again, with all of that information, the FFI library can execute the function with the arguments, throw the return value into that memory location, and then we can extract it out later. Okay, so like I said, this all basically ends up looking a bit like a struct in C, but because the types of the return value and the arguments can be just about anything, this is all very variable. So the way I implemented this is just with offsets rather than with a struct. If that was over anyone's head, I can talk later about the details of that. But yeah, that's how the library works. I also chose to use a different FFI library. In this case, it's called Dynecall. The reason for that was plain and simple. I didn't have much time to work on this, so I wanted an API that I thought I could understand. And to me, this API was very easy to understand, so I used this to implement it. Downside is its support matrix is a whole lot smaller. So this is presented a little bit differently, but there is a lot of gray here in this chart, and those are systems that are not supported. So that's one drawback. But what did it look like? So here's what it ended up looking like. The API is, in my mind, a little bit simpler than the other FFI libraries. Basically, you're just grabbing a native function from either a dynamic library or elsewhere. The next argument is the function name, which we'll find from the symbol table. And then the next two are the return value type and the argument value type. So in this case, because I'm doing my adder function, I've got double, and then double double, which, you know, if you're Canadian or from California, you know, that's an inside joke for you. Then the last line of this is, again, we're performing the addition. It just works. So this is something that works today. You can use the SBFFI module today, and this works. Obviously, many other types are supported and callbacks and that sort of thing. Okay, so is it fast? Yes. On the next slide, I'm going to show you a bunch of numbers. I just want to be absolutely clear. These are from micro benchmarks. Take them with a grain of salt. This is just an example, basically, at this point. So I put together basically the same addition example I was doing before. So most of the processing is the actual going from JavaScript into C++ and back. And of course, FFI and API, because it does a whole lot of other decomposition things, allocating buffers and stuff like that, it ended up being quite a bit slower than other things. By the way, I don't want to make this about FFI being worse in any way. Like, this is, we're standing on the shoulders of giants here. This very, very, very good and interesting code went into all these things, so I just want to make that absolutely clear. For SBFFI, it's quite a bit faster. For an API add-on, this is an example I put together that just uses Node API just kind of directly. And then I made another example that does that using the shared buffer technique that I showed on previous slides, but without FFI. And then just for extra context, I made an implementation in WebAssembly and JavaScript. Again, these are just addition functions. There's nothing too complicated here. One of the most interesting things to me is that SBFFI performed basically the same as writing an NAPI add-on, which to me, that's fantastic. That's a win. So again, take benchmarks with a grain of salt, but you know, it seems okay, right? So maybe we've solved the first problem here. Maybe it's not slow anymore, or at least for certain use cases, for certain workloads, right? Okay, but the second problem is still there, yet another dependency. So today, I have this PR open on Node Core, which implements FFI in Node Core. It's using libFFI instead of dyn-call, but it's there, it does the trick. And hopefully we can get this into an upcoming release of Node. But there are issues with that, and I'll get into those just now. But that said, you can use this today if you compile it. So this is using the built-in FFI module that I created in this PR. It has roughly the same API as SBFFI, and this is just an example of it working. So in this case, we've pulled in UV sleep, which is built into the Node process because it's in libuv. And the first argument there, rather than a library, I've put null, which is basically saying pull it from the current process, the current symbol table, rather than loading in a dynamic library. And so sleep doesn't return anything and takes in an unsigned int. So that's what we give it there. Sleep for 1,337 nanoseconds, or microseconds, and yeah, there we go. We run it, and it in fact works. So yes, this actually does work. The PR works. Amazing. Okay, there are caveats. For example, today it does not have support for callbacks. Part of the reason for that is when I implemented this, I used an API's thread safe function, which does not exist in the same way in Node Core outside of an API, so I just need to figure that out. And yeah, it hasn't landed yet. The PR is still open. Why is that? Well, one of the reasons is libFFI depends on AutoTools, in particular M4, to generate a lot of the header files for all the various architectures. And as Ben says, just say no to AutoTools. What does that really mean? It means that we don't want to add the additional dependency of AutoTools into the Node's build requirements. But maybe we do. That's a conversation for another time. Another problem I've run into is Windows, which is potentially a common theme in some of these talks. This is a bad screenshot, but basically in Windows I've run into a linker error that I just haven't had time to debug. Another problem is these fun IBM platforms like AIX and S390X, and I just have not been able to get the headers generated for these platforms yet. That's just a matter of time. So yeah, really the reason the PR has not landed yet is time. It's just a time management thing. I'm an engineering manager. I don't write code day to day. Engineering management for the engineering managers in the room, that is a lot of work, right? So that takes a lot of my time. Also, my son was born in March, my first child. That is, thank you. For all the parents in here, you know that that's a lot of work as well. So yeah, if anyone would like to help in finishing this up, please talk to me later. There's a ton of things we can do, also polish it up in a bunch of ways. But yeah, at that point, we're basically done. We have solved these two problems, and hopefully FFI will be a real thing in Node.js very soon. You'll be able to use in your projects. So yeah, they can be popular in Node.js. So I just want to thank everybody who's interacted on the PR so far. It's these folks, some of whom are in the room. In particular, I want to thank Anthony Green, who is the creator of libFFI, who has also put a bunch of useful comments on the PR as well. So yeah, that's all I have. Thanks.
Thank you. Thank you very much, Bryan. That was amazing. And I am going to say I love a shameless plug. That was a great, great shameless plug. So I'm afraid we haven't got time for questions.
Yeah, come ask me later. I'm happy to talk later.
So, and good luck landing that PR. And I do know how hard it is when you're an engineering manager to find the space and the time. So yeah, anyone who can help him out, please do.